Ever look at the world and think, how does that even work? How does a giant 1,000-ton steel ship just float while a tiny little needle sinks to the bottom? Or how does a jumbo jet actually get off the ground? Well, it's not magic, it's physics. And today we're going to pull back the curtain on the invisible rules that make our everyday world tick.
So let's start with that classic puzzle. It just seems to defy all common sense, right? You have this massive hunk of steel, a cruise ship, just bobbing along. But you drop a tiny steel needle in a glass of water, and it's gone, instantly. How is that possible? Stick with me, because by the end of this, the answer will seem totally obvious. Here's our roadmap for today. We're going to build this whole thing up from the ground, piece by piece. We'll kick things off with pressure and thrust, which will unlock Archimedes' secret to floating. After that, we'll see what happens when fluids start moving, and we'll even get into the springiness of solid objects. Let's dive in.
First things first, before we can even begin to talk about floating or flying, we have to get two really fundamental ideas straight: thrust and pressure. They are absolutely related, but trust me, they are not the same thing.
Okay, so let's start with thrust. Just imagine a huge dam holding back a lake. The total collective push of all that water against the face of the dam. That's thrust. It's the big picture total force. Simple as that.
But here's where it gets really interesting. Pressure asks a different question. It asks, how concentrated is that force? You see, you could have a massive amount of thrust, but if it's spread out over a huge area, the pressure in any one spot is actually pretty small. It's all about focus.
And this is the perfect way to picture it. Think about cutting a tomato. Whether you use a sharp knife or a dull one, you're pushing with the same amount of force from your hand. That's the same thrust. But the sharp knife's tiny little edge concentrates all that force into an incredibly small area. That creates intense pressure, and it slices right through. The blunt knife spreads that exact same force out, and you just end up with a squished tomato.
So we've got pressure down. Now let's take that idea, apply it to water, and uncover the ancient secret of how things actually float.
Think about what happens when you get into a swimming pool. The water is pushing on you from every single direction. But here's the key. Pressure increases the deeper you go. So the water at the bottom of the pool is pushing up on you harder than the water at the top is pushing down. That difference creates a net upward push, and that's what we call the buoyant force.
And this right here is the heart of Archimedes' famous Eureka moment. He figured out that the upward buoyant force on an object is exactly equal to the weight of the water it pushes out of the way. If you displace 1 gallon of water, you get the upward push of 1 gallon of water. It's a perfect trade. So what this all means is that flotation is really just a simple tug of war. You've got gravity pulling the object down with its own weight, and you've got buoyancy pushing it up. Whichever force is stronger wins the game. And if they're perfectly balanced, the object floats. And there it is. That's the solution to our puzzle. A needle is solid and dense, so it can't push enough water out of the way to match its own weight. It loses the tug of war and sinks. But the ship, even though it's incredibly heavy, is mostly hollow. Its huge bowl-like shape displaces an enormous amount of water. That creates a massive buoyant force that perfectly matches its own weight. The tug of war is a tie, and so it floats.
Okay, so we've cracked the code for still water. But the real magic starts to happen when fluids begin to move. This is how we get from floating boats to flying airplanes.
This brings us to something called Bernoulli's theorem, and it's a huge deal in fluid dynamics. The idea is actually pretty simple. If you make a fluid, like air or water, go through a narrow space, it has to speed up. And Bernoulli's big insight was that wherever that fluid is moving faster, its pressure drops.
Seriously, if you remember one thing from this section, make it this: faster flow equals lower pressure. It's this simple, inverse relationship. It kind of feels backward, but it explains so much, from how a pitcher throws a curveball to why the shower curtain always seems to billow inwards and attack you.
And yep, this is how a multi-ton airplane gets off the ground. A wing is shaped so the air has to travel a longer path over its curved top, which means it has to move faster than the air moving along the flat bottom. And what did we just learn? Faster air on top means lower pressure on top. The higher pressure underneath pushes the wing up, and that upward force is what we call lift.
So beyond just pressure and flow, fluids have their own internal, well, you could almost call them personalities. And they're based on how their molecules stick together. Let's look at two of them: viscosity and surface tension. You can pretty much think of viscosity as a fluid's thickness, or how much it resists flowing.
Honey is super viscous, right? It's got a lot of internal friction, which is why it pours so slowly. Water, on the other hand, is much less viscous, so it flows really easily.
Then you've got this other cool thing called surface tension. See, the molecules inside a liquid are getting pulled equally in all directions by their neighbors. But the molecules right at the surface, they're only getting pulled inwards and sideways by the molecules below them. This net inward pull creates a tight kind of skin-like layer on the surface. It's actually strong enough for little insects to walk on, and it's the reason water pulls itself into round droplets. All right, for our last concept, we're going to switch gears from fluids to solids and look at a property we deal with all the time: elasticity. It's the reason a rubber band snaps back into shape, and it all boils down to two key ideas: stress and strain.
So, when you pull on a rubber band, you're applying a force from the outside. The internal force that the rubber band's molecules use to pull back is what we call stress. The actual amount that it stretches as a result of your pull, that's what we call strain.
And the relationship between the two is actually beautifully simple, and it's described by Hooke's law. Basically, for most materials, up to a certain point anyway, the more stress you put on it, the more strain you get. If you double the pulling force, you're going to get double the stretch.
So let's just pull all of this together for a second. We saw that pressure is just force focused on a specific area. We learned that what floats and what sinks is just a simple tug-of-war with buoyancy. We figured out that faster-moving air creates lower pressure, and that's the secret to flight. And we even saw that solid objects have this internal battle between stress and strain. These aren't just words in a textbook. They're literally the invisible architecture of the world around us. These few fundamental rules of physics are running the show absolutely everywhere. They explain why a hot air balloon rises, how a hydraulic jack can lift an entire car, and why a golf ball is covered in dimples. The principles are simple, but what you can do with them is endless. Now that you know them, what are you going to see differently?